Hi everyone, it's John. So today I'm going to be going over the worksheet for electrochemistry. This is the first worksheet for 2C this quarter. This is in the spring quarter in 2024, so it's slightly different than anyone is seeing this in the future. That is why it's probably due to things getting switched around over the year or years. All right, so the first question that we're going to be doing here says determine the oxidation state of each element in the following compounds or polyatomic ions. So typically the way you do these is you assume certain elements always hold a certain charge, and then you look at the oxidation state of other ions. So for example, here, the hydrogen, you always assume, not always actually, but 90% of the time, 90+% of the time, you always assume that hydrogen is a +1. Or you will assume hydrogen is a +1 90% of the time. For oxygen, you also typically assume oxygen is a -2. Again, 90+% of the time. If you have to pick between carbon and oxygen, assume that oxygen is the one that's usually a -2 or something else. And then the last one is carbon. Then all you have to do is balance the charge here. So you can see we have 3 oxygens. This is a -6 total. There's a +1 from the hydrogen. The overall is a -1. So to balance this out, the carbon has to be a +4. And then the overall charge will be a -1. All right, for the next one, we have OF2. So in this case, oxygen is not the one that is a -2. You're going to assume that the halogen is actually going to be its typical state, which is -1. You can also look at it in terms of what is bonding to what. So the central atom is usually the one with the weird oxidation state, if it's a covalently bonded material or molecule. So in this case, the central atom here is going to be oxygen connected to fluorines. The oxygen here, to get a neutral molecule, since each fluorine is a -1, is going to be a +2. For the next one, for transition metal stuff, so with iron, iron has multiple oxidation states, so you have to, we don't have to do it here, but when you're naming iron, make sure that you include the Roman numeral in parentheses to indicate the oxidation state. So here, again, we assume oxygen is a -2. And then iron here is going to have to be a +3 for this to balance out to become a neutral molecule. For K2O2, now this is one of the odd ones. Well, we're not going to assume oxygen is a -2. It's an ionic material. And if you have this metal, so like a group 1 metal or group 2, those will always be +1 or +2, respectively. So here, potassium has to be a +1. It's always going to be a +1. It's in group 1 of the periodic table. And then for this to balance out or give you a neutral charge, the oxygen will be a -1. For the next one, we have S2O3 2-. So this one, we're going to assume that oxygen is again a -2. The sulfurs are kind of connecting everything. And then we just need these sulfurs to balance out the charge. So we have an overall 2- charge. We have -6 from the oxygens. We need +4 from 2 sulfurs. So each sulfur is a +2. Next, we go to aluminum bromide. Bromine is a -1. It's a halogen. It's pretty much, it's not always, but it's typically like 99% of the time, it's going to be a -1. And then for aluminum, it's a +3 to balance the charge. Aluminum is, again, actually typically a +3. The vast majority of cases. For the next one, let's assume, again, the halogen is a -1. And then we have the xenon is a +4 to balance this out. And then for this last one, we have a whole bunch of stuff here. So we have copper, nitrogen, hydrogen, H2 or H2O, and hydroxide, so a bunch of different molecules or elements, I should say. So for hydrogen, again, hydrogen is always actually going to be almost always going to be a +1, unless you're using something like sodium hydride, but hydrogens are +1. Next, next we have nitrogen. Nitrogen here is going to be a -3 because the NH3 here, the amine is neutral. So to balance it out, you have 3 +1s, and then you have -3. Then you have oxygen. Oxygen, again, we assume is a -2. And then we get to look at the charge of all of these things that the copper is kind of coordinating or bonded to. And then we determine the oxidation state. So this is 0, this is 0, this is a -2 from the hydroxides, since there's two of them. So copper is a -2. Then that's it. All right, for this next one, we have completing and balancing half reactions. So for those of you that have me in discussion, I went over kind of this whole redox procedure. I won't be writing it out all in this video just for the sake of time, but I will go ahead and just kind of follow the procedure that I gave to do these. So it says complete and balance these following half reactions. So to balance a half reaction, the first thing you want to do, I'm gonna rewrite this. And the first thing you want to do is balance the non-hydrogen and non-oxygen atoms. So in this case, it's chromium. So I needed two on the right. The next thing you want to do is balance out the oxygens using water. So I need 7 waters on the right here. Balance this out. And then I go ahead and balance out my hydrogens using H plus. So I need 14 H pluses here. And then the last thing you have to do is balance the charge using electrons. So on the left side here, we have a 2 minus and then 14 plus ones. So this is a plus 12. Over here, we have a plus 6. So you can see that there's a difference in 6 for the charge. I need the left to go down in charge. So I add 6 electrons. That balances out. And that's how you do it in an acidic solution. All right. Then for part B, you're basically doing the same thing, except going to add OHs to both sides to get rid of H pluses. Oh, and this is done, by the way. That's it. So for the second one, we're going to do the same thing with basically one extra step. I guess technically it's 2. First, you balance non-oxygen atoms, non-oxygen hydrogen ones. So that's manganese here. Manganese is already balanced. Then we go ahead and we balance the oxygens using water. Then we balance the H pluses like so, or with H pluses. And then what we do is we add hydroxides to both sides. So this is the basic solution part. You add the number of hydroxides to each side equal to the number of H pluses. So that way they neutralize. They combine to form water. Then you'll find some of these waters cancel out. So the ones on the right cancel out here. And that's a 2. And then the last thing you have to do is balance the charge. So let me rewrite this so it's a little bit cleaner. So over here on the left, we have a -1. Over here on the right, we have a -4. This means that we need 3 electrons on the left. And then that's it. All right. Next, it says balance these redox reactions. So in this one, I'm going to go to a new page here because there's not enough space. One second. All right. So the first thing you want to do here is determine what is being oxidized and what is being reduced. So that way you can write your oxidation and reduction half reactions. Double check if the electrons are on the correct side. I mean, I guess you technically don't have to figure out which one is being oxidized or reduced. However, if you're asked on a test which one is specifically being oxidized or reduced, you may want to determine that up front so you can double check your work after. So here we can see that the manganese ends up as a +2 ion. This MnO4 here, you can see the manganese is going to have a +7 oxidation state. And so it goes from +7 to +2. So manganese is reduced. Just remember, reduce is reduction in charge. Then we also have sulfur. Sulfur is going to be the one that is oxidized since it's not being reduced. All right, so now we can write our half reactions. I'm just going to start with the reduction half reaction. So we have MnO4 minus. We have Mn2 plus. First thing again, just kind of going through the checklist, you balance the atoms that are not oxygen or hydrogen. That's balanced. Then you balance the oxygens using water. So I need 4 waters on the right. Then we balance the hydrogens using H plus, and then we balance the charge, excuse me, using electrons. So over here, we have a +7. Over here, we have a +2. You're going to add 5 electrons, like so. You can also balance the charge first, quite honestly. So if you determine the oxidation states before up here, oops, up here, there is a 5 difference. You can also just balance the charge first that way, instead of doing it last here. Since it is a reduction half reaction, you are going to want to make sure that the electrons are on the left side or on the reactant side, right? Because you're giving electrons to something. So it's being reduced. That is a way to double check your work. Other if it's not, if it's on the right side, something went wrong. That's also why I recommend doing it at the end instead of just doing it based off of whatever is up here. Because if you balanced it wrong, then with your hydrogens or waters or whatever else, then you'll know right away when you balance the charge, because the charges will be weird on both sides or something. But anyways, or not equal from what you determine for the original reaction, right? There's a bunch of ways you can check your work. All right, so for the oxidation half reaction, we have the sulfur. First thing we do is balance the non-oxygen or hydrogen atoms. So sulfur, added 2 on the right. Then we have to go ahead and balance the oxygens through the use of water. So I need 5 waters on the left here because there's 8 on the right. There's 3 on the left. Then I go ahead and balance out the hydrogens using H plus, add 10 on the right. And then we balance the charge using electrons. So over here, we have a -2. Over here, we have a -4 plus 10. So that's +6. And so we end up getting a difference of 8. And we need 8 electrons on the right side here. Excuse me. All right. Next, what we have to do is add these half reactions together such that the electrons will cancel out. So I'm going to go ahead and multiply this one by 5 and this one by 8. And I'm going to add them. So I will write it out. I won't write it out for the second one, but I'll write it out for this one. For anyone who may be a little bit lost as to why I'm doing this, you want the electrons to cancel out on the reactant and on the product side. So you're using the least common multiple. Oops, 25. You're using the least common multiple of the electrons in both reactions to figure out how many you're going to want in total in each. So in this case, it's 40, right? The least common multiple of 5 and 8 is 40. So we use that. All right, now we have these both written out. So this is 40 electrons here and 40. That cancels out just as we expected. Some of these hydrogens cancel out and leaves 14 left there. And then we have some waters that cancel out like that. Everything else stays. And then your final balanced redox reaction is that. And this is done in acidic solution. So this is the answer. All right. Oops. So let's copy this and put it back, and then we can go on to the next question. All right, part B, still doing a redox. We're doing it in basic solution here. Okay. So in this problem, you have one thing that is, or it seems like, keep in mind, one compound is not one molecule of the compound. But you have one thing that is decomposing into two things, and it's a redox reaction from what they tell us. So here, what you can do is this. You can look at your oxidation states again. You can see here, chlorine is the central atom here. So if we assume oxygen is a -2, There is two of them. Chlorine is a +4. So the chlorine goes from a +4 charge and then to ClO3 minus. This here is going to be a +5 charge and then a -1 charge. So you have chlorine going from a +4 to a +5 and a -1. Now keep in mind, there's multiple molecules in any reaction you do, right? So this isn't balanced. There's going to be multiple ClO2s. So what we do is we can write, again, I'm just going to write my reduction half reaction first. You can do either one, doesn't matter. So I have ClO2 and it gets reduced into Cl minus, like so. We're just going to follow the same exact rules. Non-oxygen or hydrogen atoms are balanced here. We balance the oxygens with water. Then we go ahead and we balance the hydrogens. Then we go ahead and we balance the charge. So this is a +4. This is a -1. So we have a transfer of 5 electrons here to balance it out. Now I know this is in basic solution. I'm going to wait to add the OH until after we do the half reactions. It'll go faster. It's just slightly less steps and cancellation. So then we do the oxidation half reaction. You could do it right now if you prefer. For balancing in basic, I'm going to wait till the end just because it's, again, slightly faster. One less canceling step, basically. Oops. This turns into ClO3 minus. So same thing, balance the chlorines, balance the oxygens, balance the hydrogens, and then we get to balance the electrons. There's going to be one electron on the right here. This is 0. This is +1. So we add one electron on the right. Then we go ahead and add this is ×5. This you're keeping the same. So this is the part where I'm not going to write it out. So the electrons are going to cancel out here. So I have 1 ClO2 plus 5 ClO2s. So I have 6 in total. And then everything else is different, so I don't have to worry. The electrons do cancel out. I have 4 hydrogens. I have 5 waters. I have a chlorine. I have 5 ClO3 minus. 2 of the hydrogens are going to cancel out here. And then I have 2 waters. Yeah, 2 waters on this side, which will then end up canceling out and giving you a 3. Okay. Then what we do is we're going to add OH to both sides, equal to the number of H pluses. Again, the reason I'm doing this at the end is it just saves a tad bit of time. So we add 2 OH minuses here. Like so. Actually, my apologies. I made a mistake here. I forgot to multiply the hydrogens by 5. There should be, this is going to be 10, right? Because you're multiplying it by 5. So 10 minus the 4 here. So that's going to be 6 H pluses on the right instead. All right, there we go. So we're gonna add 6 OH minuses to each side. And then after doing some cancellations, right? So everything else is kind of the same. Really, the only thing that'll cancel out is some waters. I have 6 OH minuses here. On the right side, I produce 6 waters, and there's 3 on the left. So the left ones cancel out. And then 6 minus 3 is 3. So I have 3 waters left here. And then that's it. So then this is your full reaction in basic solution. And we're done. All right. Next, it says determine the standard cell potential for this reaction. All right. So for this problem, you just have to use the equation that the standard cell potential is the potential at the cathode minus the potential at the anode. That's really it. Now, do note here that we have a galvanic cell, and this implies that the standard cell potential is bigger than 0 because it's spontaneous. Great. So a way you can double check your work on a test is make sure if it's a galvanic cell that it's positive potential. If it's an electrolytic cell, it's going to be negative standard potential. So those are just 2 ways you can check, right? So B and D here are automatically off. But yeah. All right. So all we have to do here is calculate cathode minus anode. Just remember that cathode is where reduction occurs. And the anode is where oxidation occurs. So looking at this problem, we have silver. Silver goes from a +1 to a 0 charge. So silver is reduced. So silver is at the cathode. And we can see magnesium is oxidized. That's at the anode. And then we just have to plug in the potentials. So if you're looking at a chart, silver is at 0.80 volts. Magnesium is at negative 2.36 volts. And then we get 3.15, or with my sig figs, 3.16 volts. Again, these values that I got here come from my table. And that's it. All right, great. For the next one, we're doing the exact same thing. We can see that PB is reduced. It's going down in charge. The zinc is oxidized. So PB is at the cathode. Zinc is at the anode. So for lead 2, or lead with a +2 charge going to a neutral state, that has a potential of negative 0.13 volts. minus the anode, which is zinc. So zinc goes from a 0 to 2 plus. So that is negative 0.76 volts. And then when we add these up, we have positive 0.63 volts. The answer is A here. You're just looking at a table, doing a little bit of subtraction. It's not too bad. All right, here we can see that iodine is reduced. So again, that's at the cathode. We see that copper is oxidized. So that's at the anode. And we just plug in once again. So for iodine has a potential at 0.54 volts. Copper 2 has the potential of 0.34. So about 0.2 volts. So the table I'm having only goes to 2 decimals, but if you have a table that goes to 3, then it would be 0.195 volts. Great. Moving on. All right, so for this problem, it's a cell diagram. We can go over standard cell notation. So on the left here, we have the anode. Oops, here's a different color. Here we have the anode electrode. Over here, we have the anode ion solution, or the thing that is going to, actually, never mind. And then over here, we have the cathode. This is the cathode ion solution. And this here is the electrode. Okay. So a few things to note here is and I should also note a few other things here. So that single line is the phase boundary. And then salt bridge. So the way standard cell notation works is you always go from anode to cathode. So you start with your anode electrode, then you start with your anode solution, then you go through a salt bridge, and then you have your cathode ion solution, and then you have your cathode electrode at the end with the phase boundaries in between. All right, and there's also one here. Great. Now, a few other things to note here is you can see that this anode here has the same solution, or I guess it has an ion solution of the same element, right? Like over here. So keep in mind that when you're doing a redox reaction, right, when the anode is giving away electrons, it's becoming an ion in solution, right? You're essentially removing mass from the plate and it's going into the solution. So these can be the same. However, at the cathode end, over here, you can see these are clearly not the same, right? These are iron and platinum. So what do you do? Now, we don't actually have to calculate any standard potentials here. However, I do want to note that these don't have to be the same. The cathode electrode and the cathode ion solution doesn't have to be the same. Why? Because what happens on the cathode end is as this anode is giving electrons to the other side, the electrons go to the ions in solution. They take in these electrons and they become plated onto the electrode. So this platinum cathode is becoming plated with iron 2 and iron 3 in this case. And so again, the electrons get transferred, they go to the other end, and then they plate onto this platinum metal. So if you have to calculate a standard cell potential, use the anode electrode and the cathode ion. So don't use the electrode on the cathode side. So if you use platinum here, you would be wrong in calculating the standard cell potential. And so maybe to clarify this terminology a little bit, we can say anode electrode oxidation reaction and the cathode ion solution reduction reaction, whatever is happening. All right, and then to fill in this diagram, we're just kind of filling in stuff. So that's copper. There's copper 2 floating around here. You have a salt bridge. I don't know what's in the salt bridge. And then we have iron 3s. We have iron 2s. And then we have a platinum plate. And that's it. Yeah, for the reaction, zinc, hydrogen, and nitrate turning into zinc ions, water, and nitrogen monoxide. Describe the voltaic cell, shorthand and longhand notation in which it occurs. Label the anode and the cathode. Use a table of standard electrode potentials to evaluate each cell and balance the equation for the cell reaction. So for this, we'll write the standard cell potential first. The standard cell potential, or standard cell notation, sorry. Standard cell notation, we have zinc. We're going to again start at the anode. So zinc is being oxidized here. Then we have zinc ions in the beaker. Then we have the salt bridge. And then we have NO3 minus ions. But then what is the electrode here? So the answer is they don't give us one. So let's just use whatever we want, right? Because you can't use NO as your electrode. That doesn't really make sense. It's a gas, right? Your electrode has to be solid. So let's just pick an electrode, kind of like what we did before. Let's say they don't have to be the same. So let's just use platinum. That should be fine. Probably also use copper or something else. But you need something for things to travel through. For 2 at the cathode. All right. And then we need to calculate E cell. So this is cathode minus anode, right? So we just have to do 0.956 minus negative 0.763. And then we get 1.719 volts. So that is the potential. And then if you want to balance the half reactions, assuming this is an acidic solution, I would need to take this top one and multiply it by 3. Take this bottom one, multiply it by 2. These are balanced half reactions. Then we go ahead and add these. And then the electrons cancel out as desired. Oops, I also need to make sure that you reverse the first one. Times 3 and reverse. You get 3 Zn2 plus. And then 2NO plus 4H2O. And that's it for this one. All right. All right, this question reads, the standard Gibbs free energy change for the following voltaic cell is that at 25 degrees Celsius, what is the standard potential of the cell? All right. So what we have to do here is use this equation here, where N is the number of electrons transferred in a balanced redox reaction. Another way you can think about it is just use the LCM. That's also fair. Or the least common multiple of the numbers of electrons used for each half reaction. So do keep in mind, this is in joules. So if you have kilojoules, make sure you convert it. But not kilojoules. So if we want to solve for the standard potential of the cell here, we can do just a little bit of algebra, dividing both sides by negative NF to get that. You can pull the negative out front if you'd like, but we get this, and then we can plug in. So delta G is negative 89,300. Again, this is in joules. N, the number of electrons transferred. Well, if you write out both half reactions, so we have copper is at the anode. So we have copper turning into copper 2 plus 2E. Remember, at the anode, you have a solid going into aqueous phase, right? It's losing electrons, it's becoming ionized in the solution. And then at the cathode, you have the opposite end, or the opposite things. So we have Ag plus, you have an ion that is taking in an electron. They give you Ag. Now, the least common multiple is 2 here. So N is 2. So when it's balanced, right, I'm not going to write out the whole balancing, but N will be 2. We plug this in, negative 2 over Faraday's constant. I'm going to drop the 0.33. And then you get 0.463 volts. So the answer is A. All right. So fairly straightforward question. The next one, it says determine delta G for the reaction. So we're doing the same thing here. Now, N here is 2. Faraday's constant is still the same. For the cell potential, though, we do cathode minus anode, right? So here, let me write it out. Which one is the cathode? Which one is the anode? You can just look at the oxidation states. So you can see that silver is going from a +1 to a 0. So silver is being reduced. So Ag is reduced. Therefore, it's the cathode. And then that means that magnesium is oxidized, which is at the anode. And then we just go ahead and plug in. Now, I do want to say that this formula only works assuming that you're given them in the format like this, the standard potential. So on a table, this is how they're given. You're given the reduction reaction. So you're given the reaction where the electrons are on the left here. If you have a reaction where the electrons are on the right, and you know which one is the cathode and which is the anode, if you add the standard cell potential for that one where it's reversed, if you subtract it, so like let's say if this one was reversed, where these two sides swapped spots, and the standard cell potential was positive 2.356. If you subtract this, you're going to get the wrong answer. They have to be in this specific format where the electrons are on the left if you're doing cathode minus anode. Another way you can think about it, where the minus comes from, is what you're doing with the anode part is you're reversing the reaction, which reverses the potential. So if you had a positive potential, then it turns to a negative, and then you just add them, kind of like what you've seen before with like Hess's law, or equilibrium constants and stuff like that. Where reversing it has some sort of effect, and then when you add them, you do something with them. In this case, you add the potentials. And then when you plug this in, you get 3.156 volts. Then we just plug into delta G. So delta G is equal to -2, or the negative on the outside, negative times 2 times 96,485.33 times 3.156 volts. Keep in mind, this is in joules. So it's a 609,013 joules, or -609 kilojoules. There we go. All right, going on to the next, it says calculate the KSP of lead iodide from the following standard electric potentials at 25 degrees Celsius. So when you have a KSP, I won't do a whole KSP overview. I do have a discussion worksheet from 2A somewhere on the channel if you need to review that. But KSP is the equilibrium constant for something dissolving in water. So if you have a solid that doesn't completely dissolve in water, you'll have some KSP. So lead iodide is not completely soluble in water, and the KSP is for this reaction, or this equilibrium, I should say. So the KSP is for this. If you were to write it out, we're not going to actually need this since we just want KSP, but it is for this reaction. And this is important. All right. So essentially what we're going to want to do is, and actually, before we even get into that, let's talk about the formulas we need to use. So we're given standard cell potentials. We want KSP, and we need to figure out some way to relate them. So one equation you have with standard cell potentials is this, the one we just used. Another one that you have, which you may have not seen in a while, is this one. Remember KSP, the SP is a subscript. It just stands for solubility product. It's just a label, but it's still K. So the other reaction you have or equation you have is this. Delta G is equal to negative RT times ln of K. In our case, it's KSP here. Okay. So then what you can do is you have two equations and you have two unknowns. Is a way you can view it. We don't have delta G. We know we can figure out N. N is 2. We have Faraday's constant. We can figure out the standard cell potential. We have R and T. We don't have KSP either. So you have two equations, you have two unknowns, and you can always solve a system of equations typically by two methods from what you saw before, at least linear equations. There was elimination and substitution for linear equations. In this case, in pretty much many cases, we use substitution in the sciences because many things are not linear. So, or two linear systems. So if we use substitution here, we're basically getting rid of the delta G, plugging it in. And now I have everything except for KSP, or I can find everything except for KSP. So I can calculate KSP based on all these quantities. I just have to figure out what the standard cell potential is and then plug it in. Now, if you solve for KSP here, you divide both sides by negative RT. Then you get NFE so over RT. Then to solve for KSP, you exponentiate both sides. I'm just going to leave it as E without the cell because space. And we get that. All right. So all we have to figure out, we have R, we have T. R is your energetic constant, so 8.314. N is 2 from the things we're given. We need to figure out what E is. So how do you figure out what E is? Basically, what you're going to do is add these equations together in some way. So we want that reaction, right, up top that I wrote at first. So how do we do it? Well, to get this, I'm going to reverse this top equation, or sorry, not the top one, the bottom equation. If I reverse this one, and then add, so the first one is going to have the same everything. The second one, we're reversing the equation, or reaction, sorry. And from that, the standard cell potential also reverses. So instead of it being negative, it's positive 0.126 volts. Now when we add both of these together, and why did I reverse the top one? Or sorry, the bottom one and not the top one? Well, again, the goal is to get this reaction in the end. This is the goal. So I need lead iodide on the left. I need my iodides on the right. I need my lead ion on the right. And these PBs need to go away, which they do. So when I add these up, you can see this PB solid goes away. The electrons also cancel out. And then we're left with exactly what we wanted, or what the goal was. And then the standard cell potential here, we just add them up. So this is going to be negative 0.239 volts. And then we can plug in everything. So we have our potential, negative 0.239 volts. We have N is 2. We have F is 96,480. R is 8.314 joules per mole Kelvin. T is 298 Kelvin. And then we can just plug in here. So draw a line. KSP is equal to, and then we just plug in. So N is 2 times 96,480 times negative 0.239 divided by 8.314 times 298. Plugging this all in, you get 8 times 10 to the negative 9, about. And that is it for this problem. Now, a word of something to note is for this, make sure that you do have your sign correct. If you forget this negative here, you're going to get a very, very big number. So sometimes your math is mostly correct and just plug in wrong, or maybe if you got this or the wrong potential, if you forgot the negative, then your math is mostly going to be right, but your answer is going to be way, way off. You're going to eat to a really big power, and it's going to, you might not even have an overflow. You might not be able to plug it into your calculator, or you'll get some really big number. All right, we can go on to the next one here. All right, for this next problem, it says consider the cell where you have nickel at the anode and then copper at the cathode, and we're trying to determine what the concentration of nickel is. So here, we don't have standard concentrations. In a standard cell, if no concentrations are written, you assume standard concentration, which is 1 molar. When the concentration is not 1 molar, you're going to use the Nernst equation. So the Nernst equation is this. Where Q is the reaction quotient, and then E is the actual potential, so not the standard potential. Everything else is still the same, R, T, and F. For those of you who don't remember the difference between the equilibrium constant and the reaction quotient, they're calculated the same, almost the same way. So the equilibrium constant, as we covered before, is products over reactants, where the concentrations of products to their respective coefficient over the concentrations of reactants to their respective coefficients and whatever the balanced chemical equation is. And Q is calculated the same way. So products over reactants. Now the difference is that K, when you calculate K, it has to be at equilibrium. If the system is not at equilibrium, then you're not calculating K, you're calculating Q. So Q is just during any point in time for the system. So the system does not necessarily have to be at equilibrium. It can be. If Q is equal to K, then the system is at equilibrium, but it doesn't have to be. So here, what we do is I can write Q like this. Q is my products over reactants. Now, if you write out this equation where we have nickel at the anode and copper at the cathode, what you have to keep in mind is that at the anode, you're producing ions. So nickel is coming out as an ion because it's giving away electrons. And then you also have, let me move this over. At the cathode, you're removing ions because these ions are getting electrons and then turning into uh, solid, right? They're being plated onto the electrode. All right, typical equation of the state. Oops. So we have this. Now keep in mind with Q and with K, we don't include solids. So here we have products over reactants. We have nickel over copper. They're both to the first power because they both have coefficients of 1. But yeah. All right, so that is Q, right? You can kind of think of it as like the anode, the ion produced at the anode um, over the ion that's getting reduced at the cathode. All right. So now we can plug this into the Nernst equation. Keep in mind we have E. We're not given the standard cell potential, but we can figure out what that is. Okay. And then we find the concentration of nickel. So before I plug in anything, I'm gonna solve for it algebraically just to make my life a little bit easier here. So I subtract the standard cell potential from both sides. Oops. That. And then I'm just gonna copy this. Then I'm gonna divide both sides by the negative, make that go away. So this sign flips. So it's just a whole lot of algebra here to solve for the nickel. Then I multiply both sides by the reciprocal of RT and F. So NF over RT E minus E. And you exponentiate both sides. So as we saw before, I'm going to write it as EXP just because it's such a large thing. So EXP is the same as E. So I'm fully writing out the steps here. I'm going to skip it in the future if it comes up because it's just a lot of, again, algebra. And then you multiply both sides by the concentration of copper. And then we get this. All right, so the concentration of nickel, there is our formula, just a whole bunch of algebra from the Nernst equation. And then we just have to plug in everything. So we have N is 2. 2 electrons are transferred here. They're both +2 charge. And then F is Faraday's constant, R is 8.314. T, it's at 25 degrees C, so it's going to be 298. The concentration of copper they give us, it's the initial concentration, 0.136. And then the standard cell potential, this you get from a chart. So you would just do the standard potential where copper is the cathode, nickel is the anode, and then you would get 0.57 volts. And then we just plug in everything. 0.136. Then we have 2 times Faraday's constant, 8.314, 298, 0.57 minus 0.621. That's the one they give us. So that's the standard potential, or sorry, normal potential they gave us, measured potential. Ni2 plus. And then when you plug this all in, should get 0.01 molar. And then that is your answer. I do want to note when you plug this into the calculator, it's actually not 0.01. It's actually 0.0026, but the closest answer is 0.01. All right, the next one says determine E cell at 25 degrees Celsius for the following reaction. So this again is non-standard potential, so we're going to be using the Nernst equation. Or non-standard concentration, sorry. So E cell minus RT NF ln of Q. I'm just going to write out the ions. So product, the anode over the reactant. Right. And then we just have to plug in everything. So the standard potential of the cell, again, that's something that we would get from the table. Comes out to be 1.52 volts. And then we can just plug in everything. So 1.52 minus 8.314 times 298. The number of electrons in the balanced redox here, do be careful. This is 6, right? Because it's the least common multiple of the 2 and 3. Then we have Faraday's constant, ln of 0.435 over 2.12 times 10 to the negative third. Now, one thing I did forget for Q is the respective coefficient powers, so the 2 and the 3 here. Don't forget that. Otherwise, you will get the wrong answer. And then when you plug this all in, you get 1.467 volts. There you go. Next says find E cell at 25 degrees Celsius for the following voltaic cell. And they give us the standard potential. So we just have to plug this in. Again, we're just using the Nernst equation. So I won't write it out again. That's up here. So I'm just going to plug in everything. 8.314, 298. There's 2 electrons transferred here. 96,480. Ln. Now again, we're looking at the cathode or anode side for the product side. So we're looking at that concentration there. So 0.1. And then 0.0 0.85. Oops. Mistake I made here is that this is the half potential. So if you have two of the same element on each side, the potential ends up being zero, right? Because the cathode and the anode are the same. And when you do cathode minus anode, you get zero. When you plug this in, you get 0.0275 volts. So the answer here is C. Next, it says, what is the concentration of hydrogen in the cell if the cell potential is that? And the cell diagram is that. So once again, we are using the Nernst equation as per usual. So we have so if we write it out, we get this again, right? Concentration cell, for anyone curious about the terminology, it's just where the cells differ in concentration. It's the same thing. So kind of like what we saw above with the copper one. All right. So E of cell here, because it's the same thing, is zero, right? Because there's not a difference between the cathode and the anode potentials. They're both hydrogen. So this boils down to this. I can also rewrite Q as the concentration of hydrogen at the anode over the concentration at the cathode. So I didn't actually state it before here. For the copper, I probably should have. But you're looking again at the concentration of the anode over the concentration of the cathode, right? Because your product is producing an ion at the anode, and your reactant is taking an ion at the cathode, giving it an electron. Then we can just solve for H plus at the anode. I'm going to skip a lot of the math here, but it ends up being ENF negative ENF over RT. It's going to be E to that. And then times the concentration at the cathode. So a lot of algebra, again, I just skipped a bunch of steps. Multiply both sides by the reciprocal of the fraction, take E, move the cathode one, because we want the one at the anode, right? This one's at the anode. I'll let you verify that for yourself, or you can double check the math from the previous problem. Just doing it in the exact same way, basically, except we don't have a standard cell potential to subtract. And then when we plug this in, we just plug in everything. So H plus at the cathode is 1. E is 0.0451. N is 2, because you need 2 H pluses to form an H2. So if you balance it out, you get 2 electrons. We have Faraday's constant. And then you have R, the ideal gas, the energetic constant, and then we have 293. When you plug this all in, you get 0.03 molar, which is C. Then that's it. Okay, great. Going on to the last page, we have calculate the mass of I2 produced at the anode if a current of 2.85 amperes is passed through a solution of Ki for 56 minutes. So for this problem, we're going to assume that there's I minus at the anode, and it's giving away electrons. So the reaction we're looking at is this. Then we balance it out. There has to be two I minuses, two electrons to balance the charge. So the I minus is giving away two electrons, right, to produce I2 and give away two electrons. So the way we do this problem is you may be wondering, well, where the heck do I start, right? I'm given amps and I'm given minutes. What you can do is remember what an amp stands for. So an amp is 1 coulomb, that's how you spell it, per second. So that's what an amp is. It's also C over S, so C per coulomb, S per second. It's amount of charge moving through a point in the wire or at some point in the circuit in 1 second. So it tells you how much charge is going through. So a high amp is, or high current is a ton of charge or a lot of charge is going through that or any point in that current or in the circuit, sorry, through 1 second. And a very low current means that there's not a lot of charge moving through some points in that circuit in 1 second. So if we start with that, so we're going to do conversions here. So we're saying that 2.5 coulombs pass in every 1 second. Well, now what? So now you're stuck at coulombs and seconds. Well, what do we do now? So if you're given the unit of minutes, typically you want to get rid of this time unit. You want to see how much charge passes through. What you can do is get rid of the minutes. So I'm actually going to do something here, kind of doing a 2-in-1. I'm going to multiply by 56 minutes. The units do not cancel. So you do have to convert this into seconds. And then you see the minutes cancel out and the seconds do. All right, so now we have coulombs. So if you're given time, usually you multiply the time out, you get rid of the time unit. Not always, but we are going to want mass. So we do want to get rid of time. That's another way you can think about it. Don't want time for mass. So now we have coulombs. Now what do we do with the coulombs? Well, there's one constant that you know that has coulombs in it specifically. And that constant is Faraday's constant. So if we use Faraday's constant 96,480. It has units of coulombs per 1 mole of electrons. So for every 1 mole of electrons you have, it has a charge of 96,480 coulombs. Now you can see the coulombs unit cancels out. And now what do we do? Well, now we have moles of electrons. Great. Well, if we have moles of electrons, we also have this reaction here. This reaction also has moles of electrons right here. And now we can just do stoichiometry, just as you did in 2A. So using stoichiometry, for every 2 moles of electrons we have here, I produce 1 mole of I2. The moles of electrons cancel out. And then we convert into the mass for iodine. So for every 1 mole of I2, using the molar mass, which is 253.8 grams per mole, we get our answer. This is 12.6 which is about 13. So the answer is C. So if you're not sure where to go, start with what you're given, and then try to find constants or things that you know that have similar units that will cancel out or make things go away. And then usually path becomes a little bit more clear as you kind of use different things. I think the only thing with coulombs you use in this class is Faraday's constant. So, all right, it says a constant current of 10 amps is passed through an electrolytic cell for 90 minutes. How many moles of electrons are passed through this cell? Okay. So this one's actually significantly easier. We're actually just doing what we did a second ago. So 10 amps means 10 coulombs per second. I want to figure out how many moles of electrons. So I am going to use Faraday's constant because it has coulombs and moles of electrons. I am going to get rid of this minutes. Right. That cancels out. You can do the conversion to seconds before. I just didn't want to write it out. And then we use Faraday's constant again to get rid of the coulombs and convert to moles of electrons. We get 0.560 to 3 sig figs. There we go. Next, it says determine the metal that is deposited on a cathode. If it takes 290 seconds to plate out 0.5 grams of the metal by electrolyzing a solution containing some metal with a 3+ charge ions of a metal with 2.53 amperes of current. So for at the cathode, we can write out the equation first. It's plating on, so it's turning into a solid, right? Like so. You're essentially neutralizing the charge. Great. So the way we differentiate between things is by molar mass, right? So we're eventually going to want to figure out what the molar mass is or get units of grams per mole. That's really what we want. We'll want to figure that out. Well, we already have grams. The grams is already checked off. We have this. We don't have the moles, though. The moles of M3+. So how do we figure that out? Well, we have the amps, all right? So just like we saw in the other two, you can go from your amps or your current to charge, right? So coulombs per second. We have the seconds, the time. Then you can go to coulombs. Then you can go to coulombs to moles of electrons by Faraday's constant. Then you, after you transfer from or convert with Faraday's constant, you have moles of electrons that you can then use stoichiometry to go to moles of M3+ that it combined with, right? You're assuming that all the electrons just go to this metal. If there's other stuff, then this problem is kind of a moot point. I think there's no point in doing it, but that's how we're going to attack this problem. I'm just going to do exactly what I said a second ago. So we have 2.53 amps or coulombs per second, same thing. We have 290 seconds, so we don't have to convert to minutes here. That's nice. We use Faraday's constant, 96,480. And see this again, if you're seeing anything with mass and charge transfer or current, see this recurring theme, you're going to be using Faraday's constant. So Faraday's constant, coulombs per 1 mole of electrons, those cancel out. Then we go ahead and convert from moles of electrons to the moles of, and it's technically it's more correct to say M instead of M3 plus because we're looking at the grams of M, that form. But it actually doesn't really matter. It's a 1-to-1 ratio, right? The moles of electrons cancel out. And now you can see we get the moles of M, that form, 2.3. Which is 0.0025 moles. And then we plug into molar mass. So this is grams divided by moles. And we get 197.25 grams per mole. And then we get to look at our periodic table to figure out that this is almost there. It's closest to platinum. So, or is it gold? No. I take it back. It's closest to gold. Yeah, platinum is 195. This is 197. Gold's right next to it. Didn't see. And that's it. So, okay, keep these conversions in mind. If you have current and you're going to go to molar mass or grams or some sort like that, you are going to use Faraday's constant. Which of the following metals would plate out first? Copper, sodium, lead, or tin? The term plate out, I'm assuming what is meant is when you're plating it out, you're removing all of the ions from the solution to form a solid. So keyword, all of the ions, leave the solution, combine with the electrons, form the solid. So which one plates out first, where all the ions are gone first? Well, if you think about it in terms of how this works when it plates out, you have an electron that gets transferred to an ion that plates out, right? So presumably, if you have a current running through and you have an equivalent number of ions in different beakers with each of these, so I'm going to actually write that. So assuming equivalent number of ions in each solution, and they're separated solution. We go with the one that requires the least amount of electrons, right? So if you have a current flowing, the one that takes in the least amount of electrons is going to plate out first, right? If one takes twice as many electrons running at the same current, it's going to take twice as long, right? If it takes 3 times as many electrons at the same current, also going to take 3 times as long. So we're also assuming same currents. So the one that requires the least amount of electrons, well, copper is a 2 plus usually, or a 3 plus. Sodium is always a +1. Lead is usually a 2 plus, 2 or 4. So 2 or 3. This is 1. This is 2 or 4. And then tin is, I think, just 2. Well, the one that requires the least amount is sodium. And that's the answer. Right? Sodium requires less electrons. Therefore, it plates out first. With the same current, same number of ions, it just requires less electrons, and then it forms the solid faster than all of the others. All right, so I hope this video helps. And I will see you again in the next video.